We first note that this function has the structure of a product. So y is equal to e to the x times the cube root of x to the fifth. And fortunately, we have a rule that allows us to differentiate products, and that's called the product rule. Okay, and then the product rule tells us that the derivative of f times g is given by f times the derivative of g plus g times the derivative of f. So this is called the product rule, and we're going to apply it in this case. I'm going to let this function be f. And I'm going to let this function here be g. Okay, so y prime. So I start off by taking the function f and multiplying by the derivative of g. And I'm going to write g as x to the 5/3 with a rational exponent. So we take the derivative of that, and then we add, and then I have my function g times the derivative of f. So let's go in and make the actual calculations of the derivative. So I have e to the x times 5/3 x to the 2/3. And remember, that's just the power rule. And remember that the 2/3 that I got came from the fact that 5/3 minus 1 is equal to 5/3 minus 3/3, which is just 2/3. Okay, and that's where this guy came from. Plus x to the 5/3. The derivative of the exponential function is just itself, so e to the x. Okay, you can actually stop there. That is the correct derivative. You can also continue and do a little more simplification. So we see that there's an e to the x appearing in both terms. So you could factor that out if you wanted to, and you'd have e to the x times 5/3 x to the 2/3 plus x to the 5/3. Okay. You could also factor out the lowest power of x that appears. So that would be x to the 2/3. And that would leave me with 5/3 plus, and you might be wondering what goes here, but you just need to think, so what do I have to multiply x to the 2/3 by in order to get x to the 5/3? And then you just have to remember that, well, if I'm multiplying two numbers with the same base, I can add the exponents. So what do I add to 2/3 to get 5/3? Well, that would be 3/3, right? So 2/3 plus 3/3 would give me 5/3. 3/3 is just 1, so I'm going to have x to the first power here. And you could also factor out 1/3 if you'd like. So here I have 1/3 e to the x times x to the 2/3. And that will leave me with 5 plus. I can't just have an x here. I need to have 3x in order for the product of 1/3 times 3x in order to be equal to x. Okay, and this would be like a simplified version. So you might be interested in doing this if someone, say, asked you solve for the values of x for which y prime is equal to 0. Then this is really going to be easy to set equal to 0 and solve for x in this format. But if you're just finding the derivative, this format is fine. In this example, we want to find the derivative of h of t. And again, we have something in a product structure here. Notice that the independent variable is t, and it appears in 3t squared minus e cubed times ct plus k. We also see these other letters appearing. These are just constants, so they're just fixed numbers, and you're just going to treat them like a number, like pi or 3 or -5. Okay, so for instance, the constant rule would apply with this guy. Okay, so our variable, though, is t. So just to emphasize that point, I'm going to write, we could say that we want to find the derivative dh dt. That's the derivative of h with respect to t. Okay. So let's note the product structure here. H of t is equal to 3t squared minus e cubed times c times t plus k. So dh dt, the derivative of h with respect to t, is equal to f. So I'm going to call this function f. Looking over the product rule. So I have 3t squared minus e cubed times the derivative of ct plus k plus ct plus k times the derivative of 3t squared minus e cubed. Okay, so now let's carry out those derivatives. So the derivative of ct plus k with respect to t will just be equal to c. And then the derivative of k is just 0. So the derivative of this binomial would be 6t minus 0. I'm actually done taking the derivative at this point, but I'm just going to clean it up a little bit. So I have 3ct squared minus ce cubed plus, and then 6ct squared plus 6kt, and I can actually combine these like terms, and I get 9ct squared minus ce cubed plus 6kt, and then that's my final derivative. So this is dh dt. This function we would like to differentiate. At first it looks like a product, and at first it looks like we would want to use the product rule, but notice how the first terms are the same in both of the binomials, and the second terms are the same, and here we have a minus, here we have a plus. So this is really, if I were to multiply this out, I would have a difference of squares. So in other words, this is equal to 9x minus 1 over x squared, or equivalently 9x minus x to the negative 2. So I haven't taken any derivatives, I've only rewritten the function, but the key here is that we shouldn't just immediately jump to the product rule, because it can be a time-consuming rule to use. We should first see if we can rewrite the function somehow in a simpler form that would make the derivative easier to take. And in this case, that is the case. Now I can take the derivative, and I have dy dx is very simple. It's just the derivative of 9x is just 9. And the derivative of this term is just, using the power rule, negative 2x to the negative 3. So I can simplify this a little, and I get 9 plus 2 over x cubed, and I'm done. Some of you might be wondering, do I have to write my product rule and take my derivatives in exactly this order? You might think it'd be difficult to remember that. And fortunately, you don't have to. Since the operations involved are addition and multiplication, these operations are commutative, and that means that if I wanted to switch the order here or switch the order here, or even switch the order here, that would be perfectly fine. So you could calculate this derivative as, use the product rule as g prime f plus f prime times g. You could write it as g f prime plus f times g prime. So all I've done there is just swap these two terms. So you have a lot of flexibility. The basic idea is if you've got a product of f times g and you're taking the derivative, you just have to take the derivative of one of the functions and multiply it by the other function, and then add that to the derivative of the function that you didn't differentiate before times the other function. So that's basically, as long as you have those components, you're good. And always remember that the derivative of a product is not equal to the product of the derivatives. You have to use the product rule.